Thank you, David, and thanks very much to Finding Petroleum for asking me back to talk again as I talked about Namibia in January 2013. So as a triumph of optimism over experience, here I am again to talk about Namibia. Well, sorry, David, I'm going to start my talk about Namibia in the obvious place, Uruguay. This type of talk has got to start with a bit of regional reconstruction. Why would I want to be thinking about Uruguay at this moment? Well, the conjugate to the Namibian margin, and specifically the Lineaments Basin, which is going to be the centre of the talk today, is across on the other side of the Atlantic in the around Uruguay and southern Brazil area, and essentially it's the Playtest Basin. So the reason for looking at the Playtest Basin is to try and compare and contrast Namibia with its conjugate margin, because we hear a lot about conjugate margins. What you find on one side of the Atlantic is what you're going to go and find when you see the conjugate basin on the other side of the Atlantic. I'm not a huge conjugatist because, well, here's a good example. The two conjugate basins look completely different. This is the Playtest Basin across in southern Brazil, and this is the Lineaments Basin on the Namibian margin, and you can see that they look very different. The huge difference, I should say that that's the sea bottom, and the yellow horizon here is about the base of the Tertiary, so the top of the Cretaceous. And this is the basement. The big difference is, in fact, the amount of material that has fallen into the Atlantic from these two margins. And on the Playtest Basin here, there's a massive tertiary section, whereas in the Namibian margin, although there's quite a thick tertiary delta, it's much reduced compared to Playtest. So it is a different basin. It's not quite the same. But I think that within the whole morass of looking at conjugate margins, looking for similarities between two sides of the basin, there are some truths and there are some useful aspects that can be pulled out and will help us with our exploration. But the first thing I just wanted to say, I mean, the whole Playtest Basin is one of the largest clastic systems in the world that's virtually undrilled. It's virtually unknown. Who knows about the Playtest Basin? What do we know about it? Oh, it's a mud-prone delta and it's full of gas. That's all we know. But here we are. This is a seismic line that runs off the coast of Brazil out into the Atlantic. And you can go 350 kilometres off the shelf. This isn't off the coast. This is 350 kilometres off the shelf, and you've still got 3 seconds of sediment sitting on top of a source rock. It's extraordinary. And the comments about, you know, we've obviously gone past peak oil and all the rest of it, we're in the decline. Just not true. Or I think as soon as we start exploring out here, I think peak oil is going to get shoved into the future a long way. But back to reality. The Playtest Basin, the thing that was exciting about the Playtest Basin is we were looking for similarities between the Namibian margin and the Uruguayan margin, the Brazilian margin. And we saw some features here that were very similar and some that were very different. So this is the Playtest Basin, the tertiary section in here, and you can see some extraordinary compressional structures in the toe thrust area at the bottom part of this tertiary delta, and some extensional features in the up-dip part of this tertiary delta. And you also see a lot of fuzzy seismic, which is basically a huge gas cloud. The manifestation of that gas cloud is twofold, but largely it's this reflector in here. Now this reflector is the base of a gas hydrate layer. It's one of the largest gas hydrate accumulations in the world, and it's relatively well known. And it's basically from the seabed down to this reflector down here is essentially solid ice. So it's ice trapping methane in the gas hydrate layer, and this is the base of that gas hydrate layer, which is called a BSR. A BSR is a bottom simulating reflector, and the reason that it's bottom simulating is that it's always just about the same distance from the seabed, so it's a reflector that occurs at a set distance from the seabed. The reason for that as was explained to me by a guy called Mads Hoos, who's a professor at Manchester University. When I showed him this seismic line, he said, well, it's quite simple, really. Basically, the temperature of the water at the seabed, just about all over the world, is about 5 degrees centigrade. Doesn't really vary very much. But as you go into the Earth, the temperature increases. So when you come a certain point into the Earth, the temperature has increased enough to destabilize the gas hydrate crystals. And so at this point, methane is free. It's a free gas. So we're seeing free gas here. And at this point, methane is trapped into ice. It's a very simple principle. And it sort of unlocked a specific idea, which I thought was very interesting. And I'll come back to it in just a moment when I stop going off-piste into Uruguay and we start thinking about Namibia. Because the other thing that's interesting about the Playtest Basin is that it's this big tertiary delta in here with a decollement surface running through here where the yellow line is drawn. And this big old tertiary delta started to slip and fall into the Atlantic. So why would that be? Well, the idea that we've got is that in common with other great gravity slides that you see around the world in the Niger Delta and also in the Rovuma Delta as was shown this morning, what's happening is that at this point there's a rock with an increased amount of organic material or a potential source rock, and when the delta is built out over that source rock, the source rock starts to cook and it starts to generate hydrocarbons. That increases the overpressure on a specific layer, reduces its viscosity, and it becomes a decollement surface. So every time you see one of these decollement surfaces on this scale, it's probably telling you that there's a source rock there. In this case, it would be a Paleocene source rock, kind of a surprise for the South Atlantic to have a Paleocene source rock. And it only works in specific places where you very rapidly build out huge tertiary deltas on top of the source rock. In fact, the main source rock here in the Playtest Basin and along the south coast of South America, the east coast of South America, is going to be an Aptian source rock. And that's located down here. This is the Aptian section, way below this delta. And when this delta piles out, not only does it start to cook the Paleocene at the base of the deltaic sequence so that the whole lot becomes destabilized, but it also starts to cook the Aptian source rock, which is lying below it. And that Aptian source rock will initially generate oil, but eventually if you bury it deep enough, it'll start generating an awful lot of gas. And what we're seeing up here is an awful lot of gas. But at some point, it will generate oil. So this oil migrates up through the clastic section, hits the base of the BSR, which is an impermeable layer because it's ice. So it's a solid impermeable layer, and it migrates up underneath the BSR until the BSR destabilizes because it's too shallow. And then you get a series of oil seeps, and that's what we see on the coast of Uruguay going into the southern Brazil. You see a row of oil seeps that just about sit on top of the edge of the stabilization of the BSR. Interesting story, and the seeps that were published here are part of a study done by Infoterra, a company called Astrium. Have also got a huge data set that sits over the top of it, or they're now changed their name. I'm struggling. What is it? It's what? Airbus, obviously. Yes, so so Airbus have got the seep seams that will demonstrate this row of oil seeps that go up the margin there at the edge of the BSR. So you're still slightly wondering why you're hearing about Uruguay when we should be talking about Namibia. At some point, I'm hoping that becomes apparent. So that was a dip line through this big tertiary delta in the Playtest Basin. And here's a strike line. And this is quite interesting because this shows that going across the tertiary delta here where the delta is thickest, the source rock down here might be generating gas, and that's the gas hydrate that we see up on the BSR. But as the cone becomes thinner on either side, then presumably this will be generating oil. So really the Playtest Basin is an oil place. Everything we know about the Playtest Basin, it's mud-prone delta. That's only because it's not been drilled in the right place. And it's a gas delta. Well, that's only because people are only thinking about the big tertiary delta on either side of it. It's an oil place, so it's a big oily play, and quite interesting. So what might be happening in the conjugate margin sense? This is the Uruguayan side of the margin, and so what I've done here is reconstructed the two sides of the Atlantic, the African side and the South American side, back to the distance apart that they were about 120 million years ago, sometime in the Aptian. Once we know how far the two continents were apart by our plate reconstruction, we can look at our seismic lines. Fortunately, our seismic lines are up to 300 kilometers long, coming off those margins, so we can overlap them and look at the shape of the basement sequence at the time of the Aptian. And so here on the Uruguayan side, we can see seaward dipping reflectors in here. Further up the coast, we can see some Sin-Rift half-graben, but here we see seaward dipping reflectors becoming mid-ocean ridge or oceanic basalt somewhere around here. And on the Namibian side, we see seaward dipping reflectors going through a transition zone and into mid-ocean ridge basalt, again, just about the median line. And sitting on top of that will be an Aptian sequence. And that Aptian sequence is quite interesting because we can posit or propose the idea for it being present in the Uruguayan side. They've never been drilled because wells have never been drilled out into that far out into the basin to prove that it's there. But we can use that as potentially the source rock for the Uruguayan side. But when we come to the Namibian side, it has been drilled and it has been proven. And this all unraveled last year. So when I stood here a year ago proposing that the Namibian margin was about to have an eruption of oil discoveries, I was slightly wrong, but the bit we got right was that there was Aptian source rock, and that was proven by a number of wells that were drilled by HRT on the Namibian margin. So we're just going to have a look at those wells and what they might have found. We'll look at them individually, but this is the summary of what they did. They drilled two wells up in the north, in the southern part of the Walvis Basin, the Wingget 1 well and the Mermoo well. And the Wingget 1 well was, that's actually really difficult to say. The Wingget 1 well was targeted at an Albion prograding carbonate platform. Didn't find any porosity, but underneath it found a thick Aptian sequence. It had some little thin stringers of sand from which they extracted some quite light oil, I think somewhere in the 29-degree API oil. So mature, thick Aptian source rock. Mermoo well was targeted at a clastic sequence that was sitting underneath the breakup unconformity and in the way of the difficulty of looking for clastics beneath the breakup unconformity. They just found a basalt when they got there, but sitting on top of that basalt was a thick Aptian sequence that was reported to be mature. And then the Moosehead 1 well was drilling a carbonate sequence below the breakup unconformity, didn't find any porosity, but sitting on top of it was a thick Aptian source rock. So all of those wells found thick source rock that was mature. And so in the Walvis Basin and further south towards the edge of the Orange River Basin, you could say, well, the Aptian is proven to be present and that it's significantly reduced the risk on the presence of the source rock. One interesting component, and it picks up on something Duncan said this morning in the previous session, was that the Mermoo well was drilling for the what they thought was a clastic play down here below the breakup unconformity, and it actually went through a secondary target. It's really interesting, secondary target in the upper part of the Cretaceous, which was a clastic play. And what they found was quite decent sands, 19-20% porosity sands. Unfortunately, water wet because there was no up-dip seal to the sand that they drilled through. And the key to making the clastics work is looking for up-dip seal in some sort of bypass. And just as Duncan said, you either need some sort of structural bypass type of, or a sedimentological bypass system. And so we can have a look for what those might be in just a moment. So this is just a section through the Moosehead well. Really interesting type of play. There's a breakup unconformity running through here, looking at that dim spot underneath the breakup unconformity. Unfortunately, no porosity. So two of these wells were looking at carbonate plays. The other one was looking for a clastic play. The carbonate plays, let's face it, you wouldn't wish a carbonate play on your worst enemy most of the time, but carbonate plays are all really, really hard until you understand those carbonate systems properly. They just didn't work, and fair play to them for trying it, but they just didn't work. And going for the clastic play, exactly the right thing to do. Nice simple reservoirs, you know what you're doing with them, except this was a volcanic, so obviously you need to trim that exploration model a little bit. But the concept was right, and the concept was fundamentally based on the idea, and HRT are really good at this because their sort of background and drive is towards the geochemistry. Their idea was that the Aptian source rock would be present, it would be mature along this margin. And the reason they think that, and I happen to agree, is that if we reconstruct those two plates, as we saw in that the reconstruction, we go back to the Aptian, the Atlantic was a large enclosed sea with some restricted marine contact down through the south. This varies dramatically from the USGS interpretation of this basin, and quite a lot of the basin reconstructions that you see, which show that the southern part of the Atlantic is open to the global ocean. When the southern part of the Atlantic is, or nascent Atlantic's open to the global ocean, it's really difficult to generate a source rock because it should be oxic rather than anoxic. Unfortunately, this model here forgets the Falklands Plateau, which is only just pulling itself clear of the southern part of South America, and it's actually enclosing the southern end of this basin. It's just one big inland sea, and some people have said that this was the largest inland sea that the planet has ever known. I'm not sure if that's right, but it gives you an idea of the scale of it. A huge inland sea, very easy to make that anoxic, and to find a source rock that's present down here, it's no surprise to be looking for it across on the conjugate margin. And that's when conjugate margins make sense, is when you can have a source rock that you find on one side of the basin, you can actually look for the same source rock on the other side of the basin. So we're not looking for lacustrine sources on one side and then hoping they're on the other side. You're looking at a marine source rock that you're going to find on both sides of the basin. In fact, you'll find it all the way up the coast of West Africa. So those wells that HRT have drilled, they played very strongly back to the predictions made by Bray and Lawrence back in 1997 for the margin of Namibia. And in this model here, they basically saw that the Aptian would be mature along the whole margin in a restricted range. When you had enough clastics on top of the Aptian to get it to be mature. And if you had too many clastics, it would probably be gas condensate generative. And I think that they were thinking that maybe that's why Kudu was gas condensate. And if you had not so much clastics in the overburden, then it would be oil bearing. So this was their prediction, and it seems to support that prediction. But what we like to do is to model things a little bit closer than that sort of generalist type of idea when we're looking in individual plays along the basin. And essentially, the coast of Namibia, the margin of Namibia, is really three different basins. There's the Solf-Wolvis Basin, which is where the Wingget and Morombi wells were drilled, and then there's the Orange River Basin down in the south, which is the big Cretaceous sediment pile. But what about the Luderites? How do you know that just because you've got a mature source rock in the north and some mature source rock in the south, how do you know that the Luderites is also going to have a mature source rock presence? Not too much of an argument, but source rock effectiveness or maturity, how do you measure it? Well, this sort of plays on the idea of the complexity of the margin. In fact, it's rather a simple passive margin, this one, but it plays to the complexity because this is a line coming offshore the Luderites Basin, and on the right-hand side we have true continental crust. In fact, we can often see synrift grabens, so you've got post-rift material, synrift grabens, looks like good continental crust. As we come off the way, we come into synrift grabens, and then we come into something called transitional crust, often the area where the SDRs here, which are subaerial flood basalts, This is really a mixture of continental crust with subaerial flood basalt sitting on top of it and squishing it and rotating it. And then we come off the way into true transitional crust and out into the ocean floor basalt. This is kind of cool line, and I just mentioned this because it has a really interesting feature in here where we have the mid-ocean ridge basalt here, which gives you that sort of bobbly type of reflectivity, and then we have a flat zone going up into the SDRs, and just between the flat zone and the SDRs is a very steep feature here, which we call Jim Martin's cliff. And Jim Martin's just in here, and Jim was the first one to point this thing out. And the thing is, you see it all the way up the Namibian margin. You see it time and time again, and it relates, I think, to the first marine transgression of this margin as we go from subaerial flood basalts into marine mid-ocean ridge basalt. But I just mention it because Jim's here. So, complex bit of geology, going from continental crust, everyone knows, high heat flow, really hot, going to oceanic crust, which everyone knows is really cold, low heat flow, and then you've got transitional crust in the middle, where you think, well, it might be a bit of both, so we'll have a sort of medium sort of heat flow in the middle. And what we want to do is to try and sort of model that a little bit more intensely. The best way to model geotherms, obviously, is to drill some wells and to carefully measure the temperature, the top and bottom of the well, and understand the geotherm from actual physical measurements. But in this part of the basin, the Luderitz Basin, there are no wells. Well, there's some ODP wells which go into the shallow section, but there are no deep exploration wells. So what are we going to do? Well, we're left with guessing. We're left with saying, well, it's not high heat flow, it's not low heat flow, it's somewhere in between, and have a bit of a guess. Actually, we can do better than that. And the reason we can do better than that, and this is the connection back to the Uruguayan margin and to that Playtest Basin, is that within the Namibian section, there's a gas hydrate accumulation, and it sits just up here. It sits just up here, so it's looking a little bit closer at that. This is the same seismic section on both sides of the screen. On this side of the screen, we're seeing it with time as the axis there, so it's a very steep margin, and we're noticing here a BSR, a bottom stimulating reflector, in the very near surface section. Everybody ignores this stuff, it's irrelevant, right? But actually it's really interesting. The right hand side of this section is the same section but flattened on the seabed, and here you can see the BSR up here, so it's the base of the gas hydrate layer is up here. Curiously, it's not flat and it's not simulating the seabed reflector, so calling it a BSR is kind of a bit odd, but there's a good reason for that. And the reason is that as you go down the slope, you're going into deeper and deeper water, and pressure is increasing. And the stability of the gas hydrate increases as you increase the pressure. So as you come down the slope, you have to go to a higher temperature before you destabilize the gas hydrate formation. So gas hydrate, or BSRs, shouldn't mimic the seabed when you go into deeper and deeper water. They should get thicker, and that's exactly what we're seeing here. This is a strike line. So this one is going along one isobath, so we should see a BSR that is parallel with the seabed, and this is flattened on the base of the seabed, and you see a very clear BSR running along here. So this is the base of the gas hydrate layer. There's free gas in here, which is why the reflectivity is higher in those units at the top. And let's just zoom in a bit on that. Again, just to make the point, is that you've got the BSR running through here. So what we can do with this BSR is measure the thickness of the gas hydrate layer. And when we measure the thickness of the gas hydrate layer and we map these gas hydrates out, we know one thing. The thickness of the gas hydrate layer is a function of how fast the temperatures increased as we go into the Earth. And this is the Mads Huus brilliant bit of an idea, because that actually is the geotherm. So the rate of increase of temperature with depth in the earth is the geotherm. And so what we do now is that we convert via some really simple equations that it's all published information. The stability of gas hydrates is quite well understood. There's a few variables like salinity and so forth, but you can make some reasonable assumptions. And you can convert the thickness of the gas hydrate layer into a rate of increase in temperature with depth, or a geotherm. And so this is what we've done. We've mapped out the geotherm under the BSRs for the Lineaments Basin, and the variation that we find from the BSRs, and you can see that they varied an awful lot in thickness, but that was just pressure. And if once you correct for that effectively by understanding the stability of the gas hydrates, you come back to the geotherm. And the geotherm that you get is somewhere between 29 degrees and 31 degrees centigrade across these areas. Actually quite a restricted range. You can fiddle with that a little bit by changing the salinity assumptions and so forth, but it more or less ends up in that range from 28 to 32 degrees centigrade. What's interesting about this Namibian basin is that we've got an ODP well here, which gives us a direct way of measuring what the geotherm is in the Lineaments Basin. And there's also a well just off to the east, and that's a bit more up onto the shelf. And the geotherm that you calculate when you look at the ODP well is 30 degrees centigrade per kilometre, and the geotherm you get when you look at the bottom hole temperature from the well drill just slightly to the east is about 32, 33 degrees centigrade per kilometre. So the well data that we've got seems to corroborate that the rate of increase in that of temperature with depth in that upper sequence just continues linearly into the deeper section, which would be perhaps one of the unknowns with this technique. But it does seem to give you a corroboration that the estimates that you can make from the thickness of the gas hydrate layer can be used to estimate the geotherm. So how do you use that? Well, obviously you can chuck it into a 3D basin model. That would be a rather straightforward thing to do. Just to illustrate the point, though, on some 2D seismic, though, we've got the seabed running through here. This is the Lineaments Basin at 30 degrees centigrade per kilometre, because this data is PSDM data, so it's in depth. At 30 degrees centigrade per kilometre. Then the isotherm for 80 degrees centigrade would be this line here, 150 degrees on this line here. And this defines a window for us, which would be the oil generative window. And we've called it the Goldilocks zone because it's not too hot, it's not too cold, it's just right for oil. And that's this zone in here. So then you conflate that with your mapping of the Aptian source rock. And the Aptian section is the yellow reflector through here down to the breakup unconformity, which is the purple one. So you conflate the two, and basically you can map around where your source rock is mature within the basin. There's another section here. And again, this is the Aptian source rock coming through under the 80 degrees centigrade isotherm, and there's 150 degrees isotherm there. So this is the Goldilocks zone for the Aptian source rock in this particular area. And of course, once you know where the Aptian is hot enough to be generating hydrocarbons, you can look either side for where oil could be migrating from that and look for structures that you could migrate into. Not just structures, but we can look at the sedimentology to try and find some traps. And this is what I think Duncan was alluding to in his first talk of the day. It's all right finding clastics in the sequence that's sitting over this mature source rock, but you've got to have an up-dip seal. And this is a dip line coming down the way from the shelf in the Lineaments Basin. You see these bright reflectors in the Cretaceous, and these bright reflectors should be clastics. There's no carbonates built up in this section, so that we should be seeing clastics there. And you could get excited and say, oh, well, look, that's got up-dip termination. Well, no, it doesn't. It's this 2D line, And this could easily be a channel that's just migrating out of that particular 2D line and then back in somewhere else. It just goes up onto the shelf. And that was the problem, I guess, with that secondary target with the Mermoo well, is it just continues up dip and you just lose any hydrocarbons to the surface. When we look at a dip section across these things, these bright reflectors here, you can see they do look like anastomosing channel systems. So they do look like the right sort of clastic to be hunting for. We can be fairly sure that these are present within the basin, but you've got to find that up-dip seal. So what sort of structure could create that bypass? And Duncan said, are there any lineaments in the Namibian margin that might create that sort of up-dip bypass zone? Well, if we have some of these channel systems in here, as you go back up towards the shelf, and this is constant all the way along the Luderitz Basin, there's a huge deformation zone between the deeper basin and the shelf system. Whether it counts as a lineament in terms of something in the underlying crust, I'm not sure, although it does seem to happen above the last Sinrift graben that we see as you come offshore. But it would give a way for a mechanical or a structural bypass or a termination to these channel systems as you come up towards the shelf. That's one way of doing it. Another way of finding some sort of bypass or up-dip trapping system is really well shown in the Orange Basin. And this seismic line, which is a whapping long seismic line, 600 kilometres long, and it goes from the Luderitz Basin and down across the Orange Basin. And we've actually got data that goes further than this now. We not only have the northern part of the Orange Basin, but also the southern part that goes into South Africa, so we can see the Orange Basin in all its glory. And what it shows is that the Cretaceous section in the Orange Basin is really thick compared to in the Luderitz Basin, whereas the tertiary section is probably thicker in the Luderitz than it is in the Orange Basin. And what is interesting here is that here's a section that goes through the Kudu Field and tries the same game again. Now, we don't have a BSR over the Kudu Field, so we don't know if it is still 30 degrees centigrade per kilometre, but it seems to fit in with the offset wells in the Kudu area. So it might be. So here we've got the oil window, the 80 degrees centigrade isotherm, and then there's the 150 degrees centigrade isotherm there, and 300 degrees down here. What's interesting about this is that that's the Kudu Field here. This is a gas field. And as Duncan said, various people have come up with different ideas about where that gas has come from. What I can see down here is a Sinrift graben. Other people interpret this as being more SDRs, more subaerial flood basalts. And in between these subaerial flood basalts, perhaps there's Holterivian, lacustrine source rocks, and they would be buried right down here. So these are cooking gas, and that gas is going up and being found in Kudu. But what we're missing here is where's the oil that's being generated out of the Aptian source rock all the way along this margin. This hasn't been found, and that's because I think we're looking in the wrong places. A couple of lines through the Orange River Basin to look for the sort of traps that I think might work. One of the fascinating things about the Orange River Basin, just like the Playtest Basin where we started this journey, it probably seems like to you a long time ago, but that's where we started this journey, is that here we have up-dip, huge tilted fault blocks, rotated fault blocks in the extensional part of a massive gravity slide that's decoaling on this surface here. That surface equates to the Cenomanian Turonian, which is, as Duncan said, it's not proven as a source rock in this area because it's usually not buried deep enough, but it's enough of a source rock to be generative when you dump the Cretaceous and the tertiary sections on top of it, particularly the Cretaceous section, and it started to generate hydrocarbons, and that's forms the decolement surface for this big gravity slide here. So at the extensional part of the gravity slide, we have tilted fault blocks. That's one way of finding traps, and at the compressional part of the gravity slide, as we go off towards the west, we have these beautiful toe thrusts, and when you compare these beautiful toe thrusts to the Rovuma section, which goes the other way, but it's the same idea, then the Windjammer well would be drilled into this type of section within the toe thrust section. And what we're seeing here, these bright reflectors that are terminated, and this is the mechanical or fault-related updip trapping mechanism for the channel systems that we've seen elsewhere in the Orange River Delta. And so you generate a trapping system on beyond the last thrust, or the first toe thrust of the compressional belt, which is the mirror image of the Windjammer type of sequence. So I think within Namibia, if we can map out where on the Namibian margin in Luderitz, Orange Basin, Walvis Basin, map out where the Aptian source rock is mature and it's generative of oil, that's pretty useful. Where else could we use this BSR tool? And just yesterday, confessionally, I will say, I just had a quick look through a few data sets that we had in Spectrum. In Spectrum, we've got about 1.5 million kilometres of 2D seismic from around the world. So I just pulled out a few lines. This one was from Terrona Profunda in Colombia, just off the north shore of Colombia. And in this area here, it's like a big accretionary type prism. And you can see this beautiful BSR running across the way in this area, undrilled. So what's the geotherm? Anybody got any ideas? High, low, model driven? No, doesn't have to be now, because you can measure it with the BSR. You do the same thing in Trinidad. And in Trinidad, it's really interesting because everyone thinks that deep water Trinidad is going to be gas bearing. Is it? How do we know that? No one's drilled it. Well, we think it's going to be gas bearing. Well, if it's oil bearing. And in what will turn your mind as to whether it's oil bearing or gas bearing is what the geotherm is. And of course, we could never measure that because no one had drilled it. And here we've got a tool for telling us what the geotherm is. And when we map this out, we can map out the oil-prone belt in deep water Trinidad, which is kind of cool thing to be able to do. And even in some really odd places in the world, you can still have the same tools. This is a line here from the Andaman Sea. And the Andaman Sea has really wacky geology, passive margining type of geology, but it has these beautiful BSRs. And so we can use these BSRs here to estimate the geotherm. And that gives us something to input into the basin modelling to determine whether the source rocks in the Andaman Sea are going to be oil prone or gas prone. And perhaps we'll sort them, support that sort of information with the presence of oil seeps from SAR data, and you to build your hydrocarbon model from real observation rather than from modelled assumptions, which I think is probably the way to go. And where else do these BSRs occur? Well, this is from, I think, USGS again, BSRs that they've spotted around the world, and we've seen more than this even on our data, because people didn't really pay much attention to the gas hydrate layers. It's always a bit of a nuisance rather than it being part of your tool bag for estimating what the geotherm is in any one basin, whether it's in Africa or whether it's worldwide. So, summary of this seemingly random walk exercise. The Namibian margin has mature Aptian source rock along the whole margin, and we can now map it out using not only the new data that we've got, but also this tool of corroborating the geotherm that we use in our basin modelling. I think on that Namibian margin, the key to success is to chase clastic plays. Like chasing carbonate plays is something that could be done at some point, but let's start easy and get hard, shall we? So chasing clastic plays, looking for updip termination, either stratigraphic or mechanical via faulting or some of the major lineaments between the shelf and the deep water. And the last conclusion is don't ignore BSRs. It's a really interesting, simple piece of information that you can collect from your seismic data that can tell you about the geotherm in your basin. Thank you very much.
Thank you. Time for a couple of questions. You want to start over there, please?
Please wait for the microphone.
And though I know who you are, you need probably to let everybody know.
Okay. I'm Robin French, and I work these days for Mitsubishi Corporation. Thank you, a really interesting talk. But Is there anywhere in the world that you found this to work? The one example that you gave showed gas in an area where we should have expected oil on your
What,
thesis.
from the Kudu Field? Well,
Yes.
the Kudu Field is being charged from those either you interpret it either as a synrift section or you interpret it as lacustrine source rocks that are within SDRs, subaerial flood basalts, and it's all below Kudu. So in fact, the model that we use here would predict that the temperature is somewhere between 150 and 300 degrees centigrade where those sediments are. And that's why it's generating gas. So it's 100% correlation, Robin, that we have between the observation of the prediction of very, very high temperature for that synrift section and the presence of gas in Kudu. What no one's found is the oil generated from the Aptian around Kudu. That's not because it's not there, it's because we haven't found it yet, and that's, I think, the key to it.
Okay, just another quick one. You showed Tayrona. Now, there are some wells there. I mean, there's one drilled 6 years ago by Petrobras, and it was dry, but I don't have any details. And I don't know whether there's any connection with the huge 16 TCF La Perla field off the north of Venezuela. But surely some of these wells will have examined that gas hydrate, or is it?
Well, it's really interesting. We tried to chase down as many wells as we could that had actually drilled through gas hydrate layers because we were curious about the velocity of the gas hydrate layer and what to use in our model. And we found a few examples where gas hydrates have been drilled around the world, and we could extract the velocities to model the thickness of the gas hydrate layer. So in some places we've got wells that can corroborate the heat flow like they have in Namibia, and we can just go around the world making sure that our in fact I think in that particular basin we've already done this work, but we can corroborate the well data with the estimate from the BSR. But the beauty of the BSR is that it doesn't just sit where the wells are. Once you've calibrated it, if you will, for a certain basin, and it doesn't vary very much, the rate of increase of temperature with the thickness. Once you've calibrated it in a certain basin, then you can wander all around that basin and where you see the BSR, and you can use it as a predictive tool to spot variations in geotherm. And you can do it within a basin, or you can do it on a whole passive margin. So we can do it all the way from Uruguay right the way up to Newfoundland. So yeah, it's a really powerful tool, but it's a really simple little tool, and I like it.
Duncan, did you want to ask a question?
Oh.
One more. Sure.
Yeah. So what temperature are you assuming for the release of the hydrates inside 2 kilometers of water? What temperature are you assuming for the release of gas from the hydrates inside 2 kilometers of water?
Okay, it's because it's depth dependent, then I don't have that number in my head. I'm so sorry. But you just look at the phase diagram. That you can create a phase diagram for pressure, temperature, and the phase of the phase of the cath hydrate molecule, and it's easy to read off from the phase diagrams. And these things are all published, and it's quite well researched. But I don't have it in my head. Sorry, Duncan. I knew there would be a Duncan question at some point.
All right.
But sorry about that.
No, I think we need to move on. We're running a little bit late. Neil, thank you very much.